Arrays give us the ability to have a single value that holds many elements in it of the same type. In C, the way arrays work is a little bit different from how you're used to using them in Java or Python or another memory managed programming language. So we're going to look at what makes them different from those in memory managed languages, and then look at, well, how could we have an array of arrays through the use of pointers to pointers? So let's jump into it. In C, arrays are really primarily about allocating memory for you inside of some local stack frame. And so when you declare an array, you're specifying not only its type, but the number of elements it has typically. And using that information, the type, which tells you the width in terms of bytes of a single element, multiplied by the number of elements you want to be able to store in the array, determines how much space is going to be needed in that function called stack frame in order to store each of those elements in the frame. The very first index, index 0 of an array in C, because C's arrays are in fact 0 indexed, is going to have the lowest address. So each subsequent element in an array is going to have an address that comes after or at a higher number than or address than some lower indexed element. So 0 will have the lowest address, and elements after that will have higher addresses. If we had a character of if we had an array of 10 characters, and the first character was at, say, A1, then index 1, which would be the second character in this array, would be at A2. The third at A3, so on and so forth, for thinking about addresses. Whereas if we had an array of 10 int 16t types, so that means each element takes up 2 bytes or 16 bits, then if the first element was at A1, the second element then would be at A3, right? Because we need to add 2 bytes of space for each element that our array stores. We're going to look at the size of operator in more depth in just a moment, but in the frame where you declare an array, when you use the size of on that array's name, it will tell you the number of bytes in total that were allocated for that array. The name of an array is really just an alias for the address of the very first element of the array. So it's kind of like a special pointer we'll come to see that's got some slightly different semantics from a true pointer, but in a very similar sense, the name of an array is going to be bound to the first byte of the address of the first byte of that array's index 0. Arrays can't really be used as parameters or as subsequently arguments. You'll see that there is some syntactical sugar for declaring a parameter type that is an array, but really that's syntactical sugar for saying, hey, you can give me a pointer to some array. And that at that position, at that parameter position, you would expect some array pointer to be given to you. Whereas in other languages, you can pass arrays in the array type directly. But the key difference here is that in C, we're going to see that our local variables are going to be able to store entire arrays on our stack frames, right? So we can have an array where its data is actually in the frame of the stack versus on the heap, which is true in memory managed languages that have arrays such as Java. Your array data is stored on the heap, and you've always got a pointer to it. Whereas with C, you've got your array data being allocated in frames on your function call stack. Another key difference between arrays in C and other languages is that you can't reassign an array's name to mean something else after it's been initialized and bound inside of some function. You can't say array name is now assigned some other sequence of values or reinitialized in some other way. And so the name of an array is bound always to the first element of the address of the first element in the array. So as I mentioned, pointers and arrays are very closely related, but they are not the same. And there are some key distinctions that you should keep in mind when using these constructs in C. The array's name is the identifier to the first element, but it's not a variable. You can't change it. It's kind of like a special case of a pointer that you can't reassign to. Most pointers, or pointers that aren't declared as constant, you can reassign new values to those pointers and have them point to some other address after they've been initialized. After a C array has been initialized, you can't say okay, this array name now refers to some other address or some other starting element of another sequence of values. So a pointer is a variable, and as such, you can change that pointer, what it refers to, and reassign to it. An array is technically not a variable in the same sense of variables and how you think of them in the C language. You can use indexing and array arithmetic, pointer arithmetic, in very related ways, and these are sort of two sides of the same coin. What I want to point out is that when you're thinking in terms of pointers, and you see, so imagine you've got a pointer named A, and we're thinking about, or you've got an array named A, and you're doing some indexing arithmetic with it. So A plus I, where I is some integer value, that's calculating the address of some index in the array. Whereas if you use array subscription notation and you say A index I, notice you have to use the ampersand address of operator in order to carry out the same operation. The flip side is true when you're trying to dereference and actually read from some address in memory using either pointer arithmetic or array indexing notation. And so with pointer arithmetic, when you say A plus I and you calculate the address of some other location in the array based on its index, you have to dereference that explicitly. So you can put the star, which says, hey, whatever address is in these parentheses, the star saying, I want you to go read the address that's stored, or the value that's stored in that address. Whereas with A index I, what you're seeing is we're going to look up and do that exact same operation, but de facto, when you're using indexing notation, you want to go ahead and dereference. So I think the intuition to kind of notice here and point out is that when you're dealing with the addressing of memory, it's easier, and there's less notation involved in when you're doing arithmetic on addresses directly, because you're thinking in terms of those addresses, and that's what the first example points out. However, when you're thinking in terms of like reading what is in those addresses, using array indexing notation, it gives you a shorter hand view of it. And so these are sort of two sides of the same coin. We're looking at this same data from two different perspectives. When you're thinking in terms of addresses, you're often thinking in terms of the underlying memory model, and you're very aware of it. Whereas when you're thinking in terms of array indexing notation, it's more about accessing the data stored in the array rather than thinking at the memory level about its organization. The examples that you're seeing in the slide are showing how you can use either way to access individual elements of this letters array. The size of operator will tell you how many bytes are in a given variable or type, and so with the with this operator, it's worth noting that this isn't a true function. This is an operator just like the plus symbol is the addition operator, or just like the double ampersand is the and operator. So size of is an operator, even though you use it in ways that look like a function call. It's a special operator that gives it some access to information about your program and what you're giving it as an argument. And in many cases, that'll be the name of a type, which wouldn't have any meaning without it being a special construct, right? So size of int, when we're talking about int the type, or size of char the type, you wouldn't be able to write a function that you could give a type name like that in the C programming language without doing some tricky stuff with macros. Typically, you need to give an actual value, not a type. But with the size of operator, you can give it a type, and it will tell you how many bytes are stored in that type. You can also give it a variable name, and it'll use some magic to figure out, well, what type is this variable referencing, and it'll tell you how many bytes are in that variable's type as well. The size of operator will result in a value of size underscore t, which this is a type that you can declare. So you can have variables that will hold a size t value that you would assign the result of the size of operator. And this size, in terms of how many bytes does a size t need in memory in order to store its values, is machine dependent as well. And this gets back to the idea that if we are allocating values that could be arrays, and those arrays can be a size up to as many bytes as there are on a given machine, well, we need to be able to have a size t type that can reference the total size of memory, which on a 64-bit machine is going to be 64 bits, and so size of t or size t on a modern machine is going to be 64 bits. Right? So if you wanted to print it, you would use the long unsigned format specifier in a print t in order to know, what is the value stored in a size t, or what is the size of some array. To compute the length of an array, and especially one where you're initializing it using a literal. So notice here on this first line in this example, we've got t, which I'm saying somewhat generically. So for any type t, and in C, there aren't generic types, so this would be something concrete when you write your code. And array, one of the ways that we can work with arrays is we give an empty square bracket and we don't commit to a size here, right? We don't have to say 10 or 20 or however many elements we want in our array right out of the gates, but we'll often do that when we are specifying an array literal after the assignment operator as part of initialization that'll allow us to specify the initial elements of our array. Well, without committing to some value inside of these square brackets to say, hey, we know exactly how many items are going to be in this array as soon as it's initialized, what's a common technique that people will use in programs where you initialize an array in this way and you also want to know how many items there are, and make it easy to change what items you initialize this to after the fact, is often folks will calculate the length of an array by saying what is the size of an array that was initialized in my same frame divided by the size of t, which is the size of an individual element in my array, right? So if we're dealing with chars, right, this is very straightforward. So if size of an array returned 10, or evaluated to 10, and size of t evaluated to what the size of a char was, that would be 1, we would know that the length is 10 characters, right? But if we were storing, let's say, like the previous example, a 16-bit integer, and size of an array returned 20 bytes, divided by size of whatever type this array stores, which would be 2, we would know that there are 10 elements in it as well. So this is just a little bit of arithmetic to calculate the length of an array that you're initializing dynamically, or I shouldn't say dynamically, that's the wrong word here, that you're initializing using a literal. And the real win here is that you can add more elements to this literal initialization without having to worry about updating some count or counting the wrong number and things like that. Right? I should point out, as I mentioned, that you can't use arrays as parameters to functions in the same way that you can in other languages. And so if you try to use an array as a parameter in a function, really what you're saying is you can give me a pointer. And the length doesn't carry through with that, with a function call. So you can't actually use this trick to calculate the length of an array that was passed to some function. And because of that, you're going to see in this next slide, in this next point, we talk about needing to pass the length of an array as well as the pointer to the first element of the array in order to iterate through it in some cases. All right. So when we need to iterate through an array with pointers, and this is commonly the case when you are wanting to write a function that expects an array as one of its parameters, it never actually gets the full array, it only gets a pointer to the first element. And then you kind of have two options for how you're going to iterate through that array that are very common. First, you might have a sentinel value. And what do we mean by a sentinel value? We mean that there's going to be some character or some value at the very end of the array. Typically, this is the null character when we're thinking about a null terminated array that will allow you to know once you've read that element, if you read a null element, you've reached the end of your array. And until then, you're going to just keep reading item by item, right? And so this is the case of C strings, where C strings are those that are character arrays terminated with the null character. But you also are commonly going to pass in a length to a function. So you might have a function that says, hey, give me the pointer to the first element in an array and tell me how many elements there are, and I'll iterate through all of them. And this tends to be safer than relying upon a null character at the end. And so this is actually the more encouraged approach when writing C programs today. It just requires a little bit of extra bookkeeping and work on your part, because in most languages that you've used up until now, you're used to the length being built into like the idea of an array object. It knows how long it is. Whereas with C, you're passing around a pointer to the first element, and you also have to pass around a length to how many elements there are. And be careful that you don't get either of those details wrong. Right? And so on this example, the sum function is given a pointer, and the expectation is this will be a pointer to the first element in some array of int64s in this case. And the second parameter here is saying, tell me how many elements there are. And notice that its type is size t, which means that we expect we can use something that's calculated using the size of operators as shown here in order to make use of this function. So we give it as arguments nums, and notice, and this actually is worth pausing and noting as part of this slide, notice nums is just an array of int64t's, right? And we didn't have to commit to the size of this, even though we know looking at this code it's 4 elements. We could have added (5), and the rest of this code would have worked without having to update anything. And that's the real win of calculating a length in this way in C. But notice this is just an int64t. It's an array of nums. We're using it though, and this is valid code. This is fully type safe. We're passing that array to a parameter that expects a pointer to an int64 named x's in this case. And that's okay. In fact, this is how it's done in C. When you want to pass an array around, the functions that you're calling are going to expect a pointer to the first element of that array. All right? And then this nums length is that size of calculation that tells us, given the size of nums, which if these are each 64-bit integers, then we would expect this to be 32 bytes, right? So 8 bytes times 4 would be 32 for the size of nums, and the size of int64t would be 8. You divide 32 by 8, you get back to 4 for the length of nums, and that's what would be assigned to this nums length value. And when we look at what's going on in this code, notice that we're changing this pointer. So we're doing some pointer arithmetic. We're saying, okay, we want to initialize our sum result to be 0. And while length, which is the number of elements we need to process, minus minus, so we're subtracting from length after this expression evaluates, is greater than 0. And so that checks out. Here it would be. We're saying, go read the value stored in the pointer x's. And so by default, the very first value in x's that was referred to in the pointer's address was the first element of our array, which would have been 1 in this example, and add that to our result, which 1 plus 0 would have been 1 stored in the result. And then here is where we're doing the clever, interesting thing that we can start to do now that we have pointers in our repertoire. We're incrementing that pointer. And because C knows that this is a pointer to an array of int64 values, it's updating the address by 8 bytes, right? So this plus plus is not adding a single byte, it's adding 8 bytes, because when we do pointer arithmetic like this, the effects of pointer arithmetic are context specific to the type of data that you're operating on, the type of pointer. And here we've got a pointer to a 64-bit integer, so we're going to update the offset by 8 bytes to say that, okay, we're moving on to the next element in our array. And that's what's actually the really important thing to emphasize here and understand. We're saying, let's move to the next element in the array. We're going to increment our pointer by 1 to move to the element whose index would be 1 greater than what we're currently at, right? And that happens until we reach the end, and then the result will be returned. Now that we've seen pointers, it's worth thinking about, well, how can we have multidimensional arrays? How can we have an array that is made up of other arrays, or a pointer that points to a pointer at the start of some other index or sequence of elements in another array? And I think at this slide, it's worth pausing the video and considering the following code listing. And being very careful to try and draw out how you would imagine each of these particular array values, and then the last word pointer initializing on the frame for main. If you imagined this program is running, and you can be a little bit hand wavy about some of this, you can use arrows to say, okay, the name A is going to refer to some specific address and have some values in it, and so on. Notice that these three names, ABC and words, are arrays, and then word pointer is the variable that's a pointer type. You should then consider what happens when the loop at the bottom evaluates, and look into and think through what you would expect to be output there before trying this out in your editor. And there are two questions for understanding. What is the size of this array words? And what is the last line of output, right? So pause the video here and then try working through this. All right, well, let's diagram this out. So I'm going to set up a frame for main. And one of the things that I think is a common technique that is worth thinking about as you're trying to diagram how memory is laid out in a given C function evaluation is remember that the high memory address is going to be at the top and the low memory address is going to be at the bottom. And when variables are declared, A, B, C, these names are going to be mapped typically starting from the low address space. So A is going to be an array whose first byte is the character A followed by the null character, right? And I am going to, for the purposes of this illustration, simply draw individual arrays from left to right and then stack values on top of one another. But I want to go ahead and point out that this is not actually how you would imagine this being arranged in memory, because memory isn't a 2D structure, it's just a 1D array of byte values. And so here, if we were thinking about if A0 had an address of, let's say, 0, then the character A would have the address 0, the null character would have the address 1, and then B that we would see is made up of 3 characters followed by the null termination character, so BIG. And I'm not going to draw single quotes around these values, although typically you would think of them as characters that are ASCII values, right? So BIG are the next 4 values, and so A would be followed by the null terminating character, would be followed by B, would be followed by IG, null terminating character. And these would be addresses that are increasing as we move up main's frame on the stack. I'm drawing them left to right here just to sort of give a better sense, or make it a little bit easier to read the diagram, because it's pretty hard to read with my bad handwriting. But if I were to just say, okay, this is address 0, this is address 1, this is address 2, 3, 4, 5, and maybe we say that the low end of this address space starts at 0 for this particular frame. All right, and then what is C? Well, C is the word cake, and once again, this is a C string, so it's just going to be a sequence of characters, C, A, K, E, followed by the null terminating character. So this has a length of 5. And cool. I'm not going to draw on those addresses for now. And things get interesting at this next line, right? So at line 11, we've got a more complex declaration to deal with. And one of the strategies that the book talks about, the C book, is, or the C programming language, is how to read a declaration that's a little bit more complex like this. And they encourage you to not look at really the name of the variable or the array that you're declaring, and focus more on the types. And so with C types, you've got this really interesting, weird distinction that like part of the type can come before it, but if you're dealing with this array syntax types, like we are here, the array part comes after the variable's name. So we're going to skip over the variable's name as we read what is this type, and we're going to think, okay, and they tell you to read from the back read backwards, starting from the end and moving towards the front. So here, this is the end of our type declaration, and this is an array of. So this is array of. And if we wanted to be specific, we could say count elements or 3 elements, but I'm not going to worry about that for now. The next part of this type is this pointer asterisk. So an array of pointers to, and then chars, so single bytes. We know, because the pointers that we are initializing to are the names of arrays, that these are actually pointers to the first character in an array of characters. But the declaration here doesn't actually have that distinction or know that. It just knows that these are pointing to a character. But this gives us some insight into what this words array actually is. Notice in these earlier declarations, we'd read this as an array of characters. And this is not that. This is an array of pointers to characters. So we're going to have an array of pointers. And that's what this words array is going to be. So words is going to be an array of pointers. And I might make these a little bit larger to give myself space, because each of these pointers is going to store an address. Well, what do we initialize this to? Well, there are 3 elements of this array. And the first element is A, which is an array name. And we know that what we've just learned is an array name evaluates to the address of its first element, right? So I'm actually not going to write in the address of A, which would be 0 if we were using these, made up addresses for that. I'm just going to wave my hands and use the symbol address of ampersand or for address of A. If you use the address of operator with an array name, it's redundant, right? Because an array name already refers to the address of its first index. So this is a little bit nonsensical, but just to drive home the idea that we're talking about the address of A, and we'll draw an arrow here instead in just a moment. I'm going to drop that in. Similarly, address of B and address of C, right? So words is an array of pointers to chars, right? If we wanted to replace these with arrows, I could have this pointing to the very first element of A, this pointing to the very first element of B, and this pointing to the very first element of C, right? And if we wanted to use the actual addresses and we're using these made up numbers, this would have, the address 0 in it for A. This would have the address 2. And if this was in 6, 7, 8, 9, A. So this would have the address 6 in it. And then we would go up to this address would be B. And then we would need to start offsetting by the size of a pointer for the next starting address of the second element of words, or words index 1, would be B plus 8, because we're dealing with 64-bit pointers. So B, C, D, E, F. There's no G, so we would go around to 0, 1, 0, 1, 2, or 1, 1, 1, 2, right? So 1, 2 would be the next address there, right? And so on. Great. So now the question is, how do we think about what this next line would be, where we've got a declaration of that's even more funky looking. We've got 2 asterisks next to one another. So we think about this by, once again, following this technique of read from the back forward. This is word pointer is a pointer to a pointer. I should separate these out so that looks like 2 words. A pointer to a pointer to a char. All right, so this is a double pointer. We've got a pointer that's going to point to another pointer that's going to point to a character. It turns out this is actually how we think about what an array of pointers might be. If we think of the name words as being a pointer that's the same as the address of the very first index of this words array, notice that words refers to the first index of that array, which refers to the first index of the A array, right? And so with word pointer, let's add this to our diagram and try and imagine what it results in. So word pointer is just it's going to be just a single pointer value. So one address will be stored in this, and it will be whatever words is. Well, words is the address B, if we wanted to talk about this just in terms of addresses, right? So words is an array whose first element begins at address B in this made up memory space, right? In other words, word pointer refers to this first element of the words array. And notice that the first element of that words array is yet again another pointer that currently refers to A, right? So this idea that we can have one pointer which refers to an array of other pointers or even just another pointer is no problem. We can have pointers to pointers, and in fact, when you've used string arrays in a language like Java, you're already used to seeing this happening without even thinking about it, right? So word pointer we would think of as a pointer to an array of pointers to characters, right? And I would encourage you to think through the loop that's happening down here below. When we dereference, right? When we dereference with one asterisk, we're saying follow an arrow, right? And so when we follow the arrow from word pointer to whatever it stores, we would have the address that would refer to the first address of the A array. And when we print out that string, we would print out, the entire string for this %s position parameter of, or this position, this formatting specifier for the printf. And for %c, notice that we're saying, no, let's just print a single character here. And in order to get to a single character, we've got to follow two dereferences. So we're following from word pointer to the words array, and then from there to the character A specifically. Now, when we increase word pointer plus plus, notice that's going to have the effect of updating this word pointer to point to the next word. And this is how we can iterate through each of these C strings that's kept in an array of strings effectively named words, right? Conceptually, what I want you to try and walk away from the slide feeling is this is exactly how, if you had in Java an array of strings, you would work with an array of strings in C. The array of strings here is words, and this idea that we can have a word pointer that refers to a specific index within that array of string or C strings named words is no problem. And so this composes very nicely. All right. For reference, we've got some information on the slides here that you can follow along with if you'd like, and I'll leave that for later. So this was a quick introduction to working with arrays in C, and some of the key takeaways are arrays are just the names of the first address of a contiguous block of memory that you can use for storing many elements of the same type together in a frame on the stack. Unlike in memory managed languages, you are working with values in arrays that are stored in stack frames. And you can use the size of within a local stack frame to figure out how many elements a given array has, or to know how many bytes it takes more generally. You can't actually pass arrays as parameters or as arguments to functions and accept arrays as parameters, but you can pass addresses. And so as we looked at earlier, there's sort of two tactics that you'll need in order to iterate through an array in some function. One tactic is that there's going to be a null terminating value or some sentinel value that you're looking for to know when you've hit the end of iterating through some pointer that you were given to an array. Otherwise, you need to know the length, and that would be given to you as a second parameter to your function. That tends to be the preferred way, the safer way of writing functions in C, is to give not only a pointer to the first element of an array, but also the length that you're trying to ask that function to process. And you'll see this is a common idiom throughout many functions in the C language. Pointers to pointers, or are effectively how you deal with multidimensional arrays in C. And this comes up commonly, and we'll see when we're thinking about command line arguments. When you have an array of C strings, you're going to have to sort of mentally wrestle with this idea that you've got a pointer to a character array. And that's what an array of strings looks like in the C programming language. So with that, we'll move on and look at the arguments of a command line program and environment variables in the next video.